Here's a circle of radius 3. Now, to be able to explore circles, we need to be able to describe them. And to do that requires a context. The context we're going to use is a Cartesian grid with an x-axis as a horizontal line and a y-axis as a vertical line. This will allow us to be able to describe the various important points we can see on the circle. So, to start with, we all know a circle has begins with C. What could it be? Well, actually, lots of things begin with C. It has a centre. Okay. Now, in this case, if we're using the xy axis, the centre of this circle is 0, 0, which is also called, anyone know what it is? What are we going with O? Also called the origin. Okay, so this circle has centre 0, 0, or the origin. Now for GCSE, all of your circles are centred 0, 0, so you don't have to worry about them moving off of that point. Now the next thing we know, because we said at the beginning, is this is a circle of radius 3. Now, we don't know what the units are, so we just use the word units. Okay, so this circle has a radius of 3 units, which means every point or every line drawn from the circumference to the centre, which is 0, 0, is 3 units long. Which means that this line here is 3, this line here is 3, this is 3, and this is 3. Okay, and remember, any radius is the same length for a circle, so if I drew a diagonal line anywhere, that would be 3 as well. Now, remember, those of you who are familiar with Cartesian grids and coordinates will know that you can have plus and minus values for x, okay? Now, what you don't want to be doing is thinking, okay, well, this 3 here is in the positive x, so it's plus 3, and this 3 here is negative 3 because it's on the negative side of the x-axis, okay? A radius is a measure or a scalar, okay, or a magnitude. It doesn't have a sign, it just is 3, irrespective of which way it goes, okay? But where signs do become important is when we're describing points. So if we look at the circle, we can see that it cuts the x and y axes at 4 points, okay? There's 1 there, 1 there, 1 there, and 1 there. We can describe those, so let's see how good you are. This one here is 3, 0. Then going anti-clockwise, this one is 0, 3. This one is negative 3, 0. And this one is 0, negative 3. So that gives us our 4 cardinal points on the circumference of the circle itself. Now, if we consider our circle of radius 3, there are other ways to describe it. So we did a visual description the way before using Cartesian grid, but we can also use an algebraic method to describe it via a general form of an equation. Now, the general form for the equation of a circle centred at 0, 0, the origin, is x squared plus y squared equals r squared, where r equals the radius. Okay, so it's nice and easy to remember. X squared, y squared, and r squared. So if you find an equation that's got x squareds and y squareds in it, it usually means it's some sort of circle or an ellipse, okay? So let's have a look. So if we put radius 3 here, got x squared plus y squared equals r is 3, so 3 squared. So that means the equation of this circle is x squared plus y squared equals 9. And that's how you'd normally see it. So if you were to find or extract the radius from it, you have to remember that r squared equals 9, so r equals 3. Okay, you can always check this by going to something called Desmos or GeoGebra if you like that. Desmos.com is a really powerful graphing calculator. So if you go to Desmos.com, go to the graphing calculator and type x squared plus y squared equals 9 into it, you'll get this picture, which is a great example of the circle. And you can mess around with the number, so you can change 9 to 16 to get a 4, change to 25, okay? You can do anything you like. And if you want to get really funky, you can change the numbers in front of the x squared and the y squared, their coefficients. That will do something interesting. And there's loads of fun you can have with GeoGebra, with this and loads of other things. But essentially, just remember that equation of a circle, x squared plus y squared equals r squared. In a GCSE, the only thing that will change is the number, the radius squared, okay? The x squared and y squared will never change because your circle will always be at the origin 0, 0. So here's our circle, 0, 0, radius 3. And on the other side, the right-hand side, the two forms of the equation, x squared plus y squared equals 9, or in its full form, x squared plus y squared equals 3 squared, where 3 is the radius. Now, looking at the equations, can you recognise anything familiar about them? Let me give you a little hint. If I draw a right-angled triangle there, okay? And this is the radius. We know that's 3. And we know that's x. And we know that's y. And we know that point on the circumference is xy. Does that help? It should do, because circles are one of the great mathematical constructs that share many of different elements and topics of maths. So for example, this one, x squared plus y squared equals 3 squared. Think where you've seen squares in equations. Many of you will remember this classic, which we all know as a statement of Pythagoras, or the Pythagorean theorem, okay? And circles are intrinsically and intimately linked with Pythagoras. And the reason is because if you look at the right angle triangle we've drawn here, we pull it out here, we have a hypotenuse, we have, let's say this is our named angle, theta here, so we have an adjacent and we have an opposite. Now, in this triangle, our hypotenuse is fixed at 3 because it's a radius, and the radius is always 3. The opposite, if you look at opposite, is the vertical line, but the vertical line, because it starts at 0 at the origin, 0, 0, is y long, and the adjacent, because it starts at 0, 0 and it goes along the x-axis, is x long. So if we now state Pythagoras, we get the sum of the squares, so the sum of the squares of the two shorter sides equals the square of the long side. And there is the equation of the circle, and there's the statement of Pythagoras using the right angle triangle that we built within the circle itself. And that's how it works. Now, if you think about it, it makes a lot of sense. Because one other definition of a circle is, imagine the hypotenuse in the triangle, which is the radius in the circle. Imagine it as a clock hand. Now, if you move that clock hand around anti-clockwise or clockwise, doesn't matter which way you go, the clock hand, which is the radius or the hypotenuse, is always going to stay the same length, isn't it? So that's the definition of a circle, one of them. As it does so, what we'll notice, so let's say we start moving it. So that point ends up there. So x has now got smaller, but y's got longer. We end up in this quadrant, the second quadrant. Okay, there we've got x and y. Yes, x is negative, but we're talking about magnitude. So as we said in the other slide, we don't need the sign. Then, as we keep going, y gets smaller as x gets bigger, drops into the third quadrant, where we have a triangle now going that way, so it's upside down or inverted. Okay, and then as we keep going, so we're still going this way, because we've basically been going counterclockwise or anti-clockwise. So now we've got here, into the fourth quadrant. So as you can see, x and y change, but they change in proportion using Pythagoras, so that the radius or the hypotenuse is always the same. And that is another definition of a circle. Okay, so Pythagoras is very useful. You could argue that a circle's definition is the set of points generated by the rule of Pythagoras as x and y change, but r stays the same. And that set of points is also called a locus, which is a posh word for a set of points describing a shape. In these first examples, we're asked to find the radius of a circle when we're given the equation of that circle. And this is quite trivial. All you've got to do is remember that the general form is x squared plus y squared equals r squared. We've got x squared plus y squared equals 16. So therefore, r squared equals 16. Therefore, r must equal the square root of 16, which is 4. Okay, going for positive measurement. Same thing with this one. X squared plus y squared equals r squared. Here we've got x squared plus y squared equals 40. Therefore, r squared equals 40. So this is going to be a surd, isn't it? So we've got r is root 40. Simplifying that, we've got root 4 times 10. So square root of 4 is 2, which leaves root 10. Okay, and as we haven't been given any units, we could just write units on the end. Okay, but if there was a context question, we had measurements, centimeters, that sort of thing. Make sure you use the right measure. Next example is quite a common one as well. Is the point 3, 4 on the circumference of the circle described by the equation x squared plus y squared equals 25? So here we need to remember that an equation can also be seen as a set of coordinates or members that are the equation itself, okay, that are members of the equation. So a value of x and a value of y, that if you square them together, gives you 25. So all we have to do here is substitute 3 and 4. So the question we have is 3 squared plus 4 squared equal to 25? Because that's the x value from the coordinate, okay, and that's the y value from the coordinate, if we remember that this is an xy pair. So all we've done is we've taken the x as 3 and put it into the equation. And then we put the y as 4, and we've put that into the equation as well. And then we just work the equation out and see whether it's true. So 3 squared is 9, 4 squared is 16. Question, does that equal 25? Well, yes, it does. Therefore, we know that this point is on the circumference. And make sure you answer the question. Don't just leave it at that with a tick. You have to say, because it's asking, is the point? Okay? And that's how we do that question. So here's a slightly more difficult question. Is the point 3, 1 within, on the circumference of, or outside the circle described by the equation x squared plus y squared equals 8? Okay, so we have 3 conditions we're going to need to test for. Is it inside, is it on the circumference, or is it outside of the circumference? Now, last example, we saw how to see if it's on the circumference via substitution to see whether it's a member of the set describing the circle. So that's what we'll do. So question mark, oops, hang on. Question mark is 3, 1 part of the equation x squared plus y squared equals 8. Okay, so substituting in, so here we go, 3, 1, 3 squared, that's a 1, not a 7, plus 1 squared equal 8. Well, let's have a look. What does that come to? 3, 1. Okay, so 3 squared is 9. 9 plus 1 is 1 squared is 10. Does 10 equal 8? No. So we definitely know it's not on the circumference. So the question is Is it within or without? Okay, now to do that, we need to consider what we know about points on a circle. So if we have a circle here, we know it's centered 0, 0. Okay, we know that the radius of the circle, okay, this is, well, we know from the general form, x squared plus y squared equals r squared. So if we've got x squared plus y squared equals 8, so r squared equals 8. So therefore, r is root 8. So r is, if we simplify that, that's 4 times 2. So r equals 2 root 2 units. So that's the radius of this circle. So we need to find out how we can use that to answer our question. Okay. Now, if the point's inside it, so say the point is here, a line drawn from the center to it is going to be less than the radius. Yeah. And if it was outside the radius, a line drawn from it is going to be greater than the radius. So what we need to do is find the length or the distance between the center of the circle and our point. Okay, so we should all know how to do that, okay, via Pythagoras. So if we want to find out the length of the point, we know it is, okay, and you should already know this, that the distance between 2 points is the square root of the difference between the x plus the difference between the y's, okay? So it's just another application of Pythagoras. So we put square root there, 3 minus 0 is 3, 3 squared is 9, 1 minus 0 is 1, squared 1, that's 10. So the distance is root 10, okay? So if it's root 10, is root 10 bigger or smaller than 2 root 2? Okay, so to be able to do that more easily, let's turn this back into what we knew it was, which was root 8. It's much easier to compare them. So is root 10 bigger or smaller than root 8? It's obviously bigger than root 8, so our answer, which we'll put up here, 3, 1 is outside the circle. Okay, and that's how we do that question. Now, not only do circles play nicely with Pythagoras, but they also play nicely with trigonometry. So to have a go at playing with them and covering lots of new things, first thing we need to do is have a lovely right angle triangle. And here it comes. So there's the radius, there's one side, there's the right angle, x-axis and y-axis. Now we're going to create something called a unit circle, okay? And a unit circle is a circle of radius 1. So it allows us to label the lengths on our triangle. So we have y is one length, x is the other end, and because r is the radius, we know that that is 1. So let's take this triangle out so we can have a look at it in a bit more detail. So there's our right angle triangle. We know that radius is the hypotenuse, which is 1. There's y, there's x, there's our angle. And we'll have a named angle, which we'll call theta, which is the angle the radius makes with the x-axis. So, if we consider this triangle now in terms of trigonometry, SOHCAHTOA, we have, there's our named angle, which we need. There's the hypotenuse, which is the radius. There's the opposite, because it's opposite theta. And the other one is the adjacent, because it's next to theta. So now let's look at some trig functions. So we know cos theta is, from SOHCAHTOA, adjacent over hypotenuse. And if we look at our triangle, we know the adjacent is x, and the hypotenuse is length 1, which is why we use the unit circle. So cos theta, x over 1 is x, which is quite interesting. And similarly, sine theta is opposite. over hypotenuse. So the opposite is y. Hypotenuse is 1. So sine theta equals y. So now we have a very easy way of finding the angle a radius makes with an x-axis. Because if we know the x-coordinate, we can use cos theta. If we have the y-coordinate, we can use sine theta. Now to do that, we're going to need to use the inverse functions, aren't we? So, if cos theta equals x, theta is going to be inverse cos of x. And if we have the y-coordinate, we know that sine theta is y, so theta is inverse sine of y. And given that we can do that, and we can find the length of any radius, it means we can use something called polar coordinates, but you don't use those to A level. Now the other thing these do is they allow you to consider what's the first trigonometric identity. Okay, so an identity is something you can substitute for one part for another part. Okay, so you've only found one of those before, which is the difference of two squares. So we're going to look at the Pythagorean identity. So take our triangle out. We've got 1, y, and x. Now we know through Pythagoras that we can say x squared plus y squared equals 1 squared. But if you look above, where we've messed around with the trigonometric functions, we've got cos theta equals x. So we could substitute into there. And we have sine theta equals y. So we can substitute into this. So instead of x, we're going to write cos theta. So always put a bracket. There's our cos theta. It's being squared. Y is sine theta. So we'll write sine theta in there. And we'll square that. And we know that 1 squared is 1. Now we don't write identities like this. So what we do is, and it's just a nomenclature, the way we write things in maths, we write cos squared theta that way. Okay, so the squared goes above the function. Plus sine squared theta equals 1. So here we use the 3 equals because it's an identity. That is our first Pythagorean identity. Very useful when you're solving trigonometric equations. I hope that's been useful for you then as an introduction to circles and how they interact with Pythagoras and trigonometry. Next video, we'll look at how circles and tangents play together. Okay, bye-bye. I should just point out, after someone watched this and asked me a question, is that this applies to the unit circle, so where the radius equals 1. Okay, so if the radius was something else, 2, 3, 5, whatever, you'd have to adjust all the working here so that wherever I've used 1 as a radius or as a hypotenuse, that would have to be whatever the radius of the circle was. The math still works fine, but just be aware of that. Okay, bye.